because our element 1 is connected to node 1 and node 2. So where can we have displacements?
2.
Oh, well, maybe I should ask which direction, x or y, for element 1. Can we displace in the x for element 1?
Yes.
Can we displace in the y? No, because it's, remember, the truss element's a two-force member. It's axial loading only, right? So that means we're going to put, we can do K1, 0, minus K1, 0. Y is going to be all zeros. This will be minus K1, 0, K, 0, and all zeros. Okay. Does that make sense to everybody? Right? Because we can deflect in the X at node 1. We cannot deflect in the Y at node 1. We can deflect in the X at node 2. We cannot deflect in the Y at node 2. And then for the Y-axis, we can have no deflection for any one of them. Okay. So that's K1. Let's see. So element 2. So and remember, this matrix is for one that's aligned with the axis. So K2 is also aligned with the axis. So what's it going to look like? Is it going to be exact? Let's see, what's my elements? K2. So this is U2, U2, U3, U3. Is it going to look exactly the same?
Opposite rows.
Well, it'll be, yeah, down in the opposite corner, right? Yeah. So you got it. So we'll do zeros across the top. Yeah, because this is in the vertical axis as opposed to the horizontal axis. So this is K2 minus K2. Okay. Then we have K3. Am I still on the page? Yep. Okay, so what's K3 going to look like? This one is at an angle, so are we going to use the same generic matrix form, or do we have to go to a different one? We're going to go to a different one. Yeah, we're going to do sine and cosine. We want to look at the example 3.10. I don't know if you call these the matrix 3.10, not the equation. I'm used to calling everything an equation. Anyway, so we're going to look at 3.10 to do K3, right? And we need to know an angle. Does it give us an angle, or we can figure it out, I suppose. So we're going to have to figure it out because they don't tell us what it is. So I'm just going to cheat and tell you
3060.
theta equals 126.9 degrees. So cosine of that will equal minus 0.6, and the sine of that will equal 0.8. Okay. So if we went through that, doing the cosine squared and cosine times sine and all that stuff, this is what you would end up with. Minus let's see, we're going to 2 and 4. Okay, so that's all those numbers. So now what's left to do? I didn't expand any of these.
Well, we can cancel out the stuff that,
Well, we have to set up our 8x8 first. So all of these would need to be expanded out to 8x8 so that we can then add them together. Right? Like I did. Right? We started out with this, and I expanded it out to a 6x6. And I created 3 of those for this one, or for that example. So we would expand all of these out so that we could then create, you know, a large matrix like this. Or add them together to create that large matrix. But I'm not going to write out the expansion because we just be here all day. So I'll write out the 8x8. So this will be big K. Hopefully I don't screw it up. Oops. K2, 0, minus K1. Two, 3, 4, 5, 6, 7, 8. Next row is all zeros. And we'll squish this in here. K1 plus 0.36, oops, 36 K3. This is a minus 0.48 K3. 0, 0. Yes, the problem with writing these out. K2 plus 64 K3. This one is 0. This one is minus K2. zeros. Okay, a little tough to read, but you get the idea. So now what do we do? What did we do when I was going through that other one? We're gonna do, now that we've got to this point, we can do boundary conditions, right? So we can start eliminating. So we know that node 1 is going to be 0 displacement in the U and the V. Node 3 and node 4 are 0 displacement in the U and the V. Right? So that means we got, so let's see. So U1, V1, U2, V2, U4, and V4. No displacement. So we're going to reduce down to so what do those two displacements equal? Yep. That's the only place that we have loads, right? And let's see, this is a minus 4,000 because it's in the minus x direction. This will be 8,000. It's in the plus direction.